Thanks again to Bridget, Inbal, and David. Great insights there. All right, now are you ready for a fun ride? An autonomous ride, of course. It's my pleasure to bring to the stage Overland AI co-founder and CEO Byron Boots, who's going to share his vision for the future of autonomous vehicles. Byron also serves as the Amazon Professor of Machine Learning at the University of Washington. Take it away, Byron.
Wow. That's probably the craziest introduction I've ever had. Well, thank you so much for inviting me here. It's a great honor to talk a little bit about something that is near and dear to my heart, which is off-road autonomy. So I'm Byron Boots. I'm the CEO and co-founder of Overland AI. I'm also a professor at the University of Washington, so please excuse my presentation if it's a little bit professorial. So let's see. Okay, so the screen is so big. This should be fun. All right, so the first thing that I want to just kind of get into is what is off-road autonomy? And the way that we're defining it is that it's basically anything where we're driving a vehicle off-road. And off-road in this case means not just like dirt road or gravel road or double track or something like that, but also completely off-road, no roads whatsoever. So the concept is pretty simple. It's just we want to get a vehicle from one point to another, and it is going to use onboard sensing, so things like cameras and LiDAR, and onboard compute in order to choose a path to get to the goal. Okay, so I want to just sort of start out by providing a little bit of context for the type of vehicle that we're talking about here. So this is one of the vehicles that we've been using in our work. This is a Polaris RZR side-by-side. It basically, you can see right up at the top, there's a cluster of sensors, so that's where the cameras and LiDAR are. And then behind the front seats, there is a compute box. It's the big tan box. That contains a significant amount of compute, which is processing that data and then making decisions on the vehicle so it can find its way through the environment. So I think this is super cool. Most people who look at it think it's pretty neat to think about how to get a vehicle in totally off-road terrain, but why? Why would anyone want to do this? We have roads. Why do we need off-road autonomy? And to answer this question, I want to just kind of step back and think a little bit about the history of self-driving cars. So people have been working on self-driving cars since the 1980s, but there's really this turning point which happened around 2001. So in 2001, there was the Congressional Defense Authorization Act, which stated that it should be the goal of the armed forces to achieve the fielding of unmanned remotely controlled technology such that by 2015, 1/3 of the operational ground combat vehicles are unmanned. The thing which was really exciting about this, I was an undergrad when this came out. No one really knew how to build a reliable self-driving vehicle which could drive for a really long distance. And so the fact that Congress was saying this is kind of mandated that we think about this, it was exciting for someone who is, a young roboticist like myself. So the truth is, no one knew how to do this. This is still a major challenge. No one knows how to do it yet. It's something that we've been working on a little bit. Oops. Uh-oh. There we go. So what happened was DARPA, so the Defense Advanced Research Projects Agency, came up with something called the Grand Challenge, and some of you may know about this, to try to help to solve this problem. And the Grand Challenge, there's actually two of them, one in 2004 and one in 2005. The motivation was to try to get just a team of people to build a vehicle that could travel up to like 132 miles totally autonomously, and do this on these dirt roads in the desert. And so this was again a pretty neat time in robotics, in that there were these teams from universities, from companies, just hobbyists who came together to build all sorts of vehicles to try to overcome this challenge. And you can see some of the vehicles up here. There's just like a wide variety of vehicles. There's a CMU vehicle in the upper right, and a vehicle from Oshkosh in the lower right. Totally different types of vehicles, different sizes, and they all went out there and attacked this problem. And in 2005, several teams succeeded. It was amazing. They were able to actually drive the 132 miles and do it at a fairly fast pace, and essentially win the grand challenge. And these teams and these vehicles basically turned into the self-driving cars that you guys all can see on the road today in San Francisco and Phoenix and other places. There's a direct lineage here. So many members of these teams went and founded the research groups at places like Google and Uber and Aurora that actually put together these cars. So one of the things that happened, though, between 2005 and now is that these companies really focused on-road self-driving, and they doubled down on road networks and some of the advantages that gives them for developing an autonomy stack. And I want to talk about this a little bit. I think it's pretty important because the way that autonomy stacks are now structured for self-driving is just highly dependent on roads. So for example, these self-driving cars and trucks, they are operating in urban and highway environments, and they're making use of the fact that roads are precisely engineered in order to be simple to drive on, so that driving is repeatable and predictable. They're also using detailed maps. So road networks have these detailed maps, right, that allow you to figure out how to get from one point to another. And the autonomy stacks themselves are very lane focused. So when you're thinking about how to actually drive a car on the road, you're thinking about, what lane am I in? How far away am I from other drivers in my lane? When should I switch lanes? How do I use this lane in order to make a turn or get to my goal? So this structure that's inherent in the environment is very, very important for making these stacks work. There's also GPS and high-quality comms that allow vehicles to precisely localize. And there's massive data sets that are collected in these urban environments and on highways that allow you to train computer vision algorithms and things like this. Okay, so like all of that's great, but basically what happened was we went from these DARPA racer program with all these crazy vehicles which can handle all kinds of different conditions to a very specialized set of self-driving vehicles that are focused on trucking and taxis. And so my view is this is a very narrow view of what self-driving can actually accomplish. And you'll notice that defense was the original motivating technology and is nowhere to be found in sort of now current on-road self-driving applications. And so I think we're leaving on the table things like defense, self-driving for trucks which are operating on ranches, construction, agriculture, emergency response, conservation, and so on. And if you look back at all of these old vehicles, you can see that they're actually extremely capable, and they might be able to tackle some of these areas. Okay, so I want to talk a little bit about what makes off-road self-driving challenging and some of the things that we think a lot about both at my university lab and at our company, Overland. So the first thing is that there are no roads in off-road. That means that you're missing this huge piece of structure that on-road self-driving companies are taking advantage of. The second is we want to maintain high speeds so that the vehicles are useful. Third, we want to match the capability of vehicles in off-road terrain. So I was showing you the Polaris RZR vehicle earlier. That vehicle is extremely capable. So it can drive not just on dirt roads, but on extremely steep slopes, like ones with 70-degree grades. So something just to kind of, or 70% grades. So something to think about, like The steepest highway in the US is like a 7% grade, and the steepest road in the world is like a 37% grade. So if you're on one of these vehicles on like a 70% grade, it's pretty wild, right? Like you're going down a hill and just seeing the ground come right up at you. One of the things which is really hard about off-road driving is all of the terrain that you're encountering. So you have to be able to contend with ditches and wet crossings, rocks, and vegetation. Vegetation is particularly interesting because it's something which occupies space. It's like an obstacle, but you can actually just drive right through it. Whereas a rock, which is of a similar size, might be lethal for your vehicle. And so you have to be able to differentiate between the semantics of these different types of objects and terrain and understand the capability of the vehicle as it pushes through it. You also have to understand how to deal with visual distractions. So there's like dust and smoke and fog, which might be in these environments, and complex terradynamics. So the vehicle dynamics change as you're going from one type of surface to another. And if you don't account for that, bad things will happen. And then finally, in off-road environments, you may not have access to GPS or continual communication links, and that makes things like localization more difficult. All right, so I just want to show you an example of off-road driving. Here's an example of one of our vehicles out in the Mojave Desert. It's trying to drive from one blue flag to another one. There's actually a whole series of them. They're several kilometers apart. And I want you to look at a few things as you look at this vehicle driving. So first of all, you can see there's no like real road. You can see there's a big canyon over to the right that you want to avoid. And then you have to differentiate between this brush, which you can actually drive right through, and rocks, which are kind of popping up all over the place, and you definitely don't want to hit. So a small rock of maybe just like a foot high can break a control arm on this vehicle, just like rip a wheel right off. And you'll note that the vegetation, you can just kind of drive through it. And you can see the blue flag up there that we're headed to with this vehicle. And this is all real-time speed as it's driving. Okay. So how do we do this? I just want to give you sort of two ideas. So the first is that when we're thinking about how to traverse terrain, the abstraction is very different than thinking about things in terms of lanes. Instead, we think about things in terms of layers. So there's a ground plane, so some supporting surface, which we try to estimate, which allows us to understand hills and ditches and things like that. That's the minimum elevation here. The maximum elevation gives us the size of objects which are on that surface, and we also try to understand the semantic content of them. Are they bushes, trees, rocks, and so on? And then ceiling is really important because as we're driving through the environment, we have to go underneath tree branches and things like this. Another just idea that I want to throw out here is one of thinking about how to control a vehicle. And so what we do is we simulate how we think the vehicle will move through the environment by rolling out many possible trajectories that the vehicle could take. We evaluate each one of those trajectories based on our predicted dynamics of the vehicle on terrain and also the cost of driving through different things. So a tall bush would cost more than a short one, and a rock will generally cost more than a bush. So we're doing lots of simulation at each point in time, trying to predict how the vehicle will react. All right, so I just want to summarize here, and then I'll show you a highlight reel of some of the stuff that we've been able to do. So we're developing new approaches to perception, planning, and control. We're trying to drive the vehicle through an environment just using onboard sensing and compute, so we're not relying on detailed maps or GPS. Our focus is on point-to-point navigation, just trying to let the vehicle go to some point in the environment. And this has a lot of different applications, including with defense, agriculture, emergency response, and so on. And with that, I will just let this highlight reel play a little bit while I answer any questions if there's time for them. One thing I'll just mention in this highlight reel is that you will see someone in the driver's seat for a number of these clips. That person is a safety driver, so from early on in the program, we've had folks like behind the wheel ready to take over in case there's any issues, but the car is still driving itself completely autonomously. All right, thank you.
Cool, thanks, Byron. I think we have time for one question, so think about that while I ask Byron a question, which is, what's the worst accident that's occurred? Has this gone off a cliff, been sunk in a river?
No, not too many bad accidents. Basically, the vehicle has tipped over before, but there's a roll cage, and if there's a person in the vehicle...
Whoa, that looks intense. Okay.
Yeah.
So you haven't lost one yet?
No, we haven't. It hasn't like escaped from us, and everyone has been like very recoverable. You just got to pop it back up. We have done things like shredded tires and occasionally lost a wheel, but nothing too terrible.
Nothing too terrible. Well, it's interesting because Todd mentioned at the GeekWire, we've been looking over past GeekWire summits, and we were talking about this technology back in 2015. In fact, the Seattle venture capitalist Nick Hanauer and former Zillow CEO Spencer Roscoff at the time said the big thing coming in the next 3 years, so by 2018, was going to be autonomous vehicles. And the venture capitalist Nick Hanauer even said at that time his 15-year-old was going to be the last generation ever to get a driver's license. That obviously hasn't happened, so I'm curious, like, in your mind, have we had too many fits and starts, and why has it maybe been slower to see more mainstream adoption of autonomous vehicles?
Yeah, that's a great question. I think that autonomous vehicle technology has advanced quite a bit. So I think self-driving cars are actually pretty good. For on-road driving, people are trying to just drive down that long tail of all possible ways in which a vehicle can fail. That's been challenging, but I think current solutions are actually pretty great. It's another question about whether or not self-driving companies are sustainable as businesses, and I think that we're seeing some companies fail right now, but the technology itself, I think, has advanced a huge amount and is in actually a pretty good state.
Yeah, these are capital-intensive businesses for sure. We have one question straight up front.
Hi, yeah, this is completely out of my wheelhouse, so I'm kind of shooting in the dark here, but thinking from the lens of emergency response, how are you accounting for variable payloads? Like thinking from a helicopter going to pick up someone in desperate need of help, the weight changes, there's also weather to think about. How do you and your team think through those?
Okay, so I think there's kind of two parts to this. One is that if we know what the weight is, we can update the model of the vehicle in order to account for that. Same thing for if we move sensors around or change vehicle, we can just update the model of the vehicle, and our autonomy still works. For smaller changes, so like if it's a small fraction of like the weight of the vehicle or the size of the vehicle adapts online. So it's able to essentially observe its own performance and be able to adapt its controller to handle some of these unexpected changes.
Great. Let's hear for Byron Boots. Overland AI. Thank you, Byron, for being here.